In this video, we'll look at two of the ways that we quantify circular motion. We'll look at tangential velocity and angular velocity. For describing the velocity in circular motions, we have two different ways that we can do that. One is tangential velocity, which focuses on how far the actual object travels, something called arc length. And then there's angular velocity, which focuses on the angle through which the object sweeps, kind of like the size of the pie piece, if you will, that the object moves through. Tangential velocity focuses on the object itself and the curved path that it follows. It's measured in the units that we're familiar with, like meters per second. You can think of it as being very similar to velocities that we calculate in linear motion, in that their calculations are kind of similar. For linear motion, we had velocity equals delta x over t, where delta x is the displacement of the object and t is the time it takes to move through that displacement. All we're going to do is change what's on top of this expression. So instead of the velocity being equal to the displacement over time, it's going to be equal to how far around the curve it travels divided by time. That distance around the curve is abbreviated S, and it's called arc length. It's the actual distance that the object travels as it goes around the curve. If you need to know a little bit more about that and want to see what arc length is, go back and watch the circular motion video. I go into a little bit more detail about what it is in there. The arc length part of it is not usually a given in a problem. It doesn't usually say it covers an arc length of 5 meters, an arc length of 15 meters. It's something that actually has to be calculated. And because of that, it tends to make these problems a little bit more difficult than what the linear velocity problems were. Even if you had to calculate a displacement in linear velocity problems, that wasn't all that challenging. Taking any of the vectors that were in the same direction, adding them together, vectors that are opposite direction and subtracting them, just figuring out what the displacement was and then using it in that velocity equation. This time we have a whole separate equation that we use to calculate that arc length. It's based on the angular displacement. And again, I talked about angular displacement in the circular motion video. It's the angle in which the object moves through, sometimes measured in degrees, sometimes measured in radians, or it's the number of revolutions that the object has done. That's angular displacement, and the radius, how far away from the center of rotation it is. The equation is pretty straightforward. Angular displacement is equal to the arc length divided by the radius. Again, the arc length is abbreviated S. It's going to be measured in something like meters. The angular displacement is going to end up being in radians, and it needs to be in radians because if it's not, we're not going to get meters for our answer. Our radius should match the unit that we're looking for our arc length. So if our arc length is in meters, again, our radius is going to have to be in meters for that to work out. So no matter what, you're going to want to go into this equation using radians as your angular displacement. And you're going to want to use meters most likely as your radius. If you're given revolutions or degrees, make sure that you convert it. So let's figure out what the arc length is of an object that sweeps through 40 degrees at a distance of 1.5 meters from the center of rotation. First, the 40 degrees, that is our angular displacement, theta. The 1.5 meters from the center of rotation, that is the radius. Do make sure that you're working with the radius here. Some questions will give you diameter and not be so obvious about it. It might say something like a merry-go-round that's 3 meters across. If they're saying that, 3 meters across means side to side. That's the diameter. Make sure you divide that in half to get your radius. So be careful about that number. This one says a distance of 1.5 meters from the center of rotation, so we know that that's already a radius. We want to figure out what the arc length is. We want to figure out S. Now, again, we need radians to do this. We have degrees, so we have to convert from degrees to radians. We can do this with dimensional analysis. 40 degrees times and a fraction bar. The numbers that go into the fraction are basically just the two equivalents from a circle. A circle is 360 degrees, and it's 2 pi radians. So the 360 degrees is going to go on the bottom so that the degrees will cancel out. And the 2 pi radians will go on the top so that we're left with radians when we're done. I didn't put it in there, but this would be radians. You're going to have to multiply by the number on the top and divide by the number on the bottom because there's no 1 in here that we can ignore. So it's 40 times 2 pi. And again, I like to push equals after I put that in the calculator. Divided by 360. 40 times 2 pi equals divided by 360 is 0.7. I rounded that just to match the significant figures in the first number here, the 40 degrees. Again, the degrees cancel out. All you're left with is radians. Once you've done that, you're ready to use the equation here, the angular displacement equation here. The angular displacement is equal to the arc radius divided by radius, or arc length divided by radius. Substitute. Our angular displacement is 0.7 radians. Our arc length is what we're trying to find. The radius is 1.5. Multiply both sides by 1.5 to solve. So 1.5 times 0.7 is 1.05, or really 1 if you want to keep your significant figures going. And that will be in the same unit as your radius. It's going to be meters. So the arc length is going to be what we're going to use in our calculations of tangential velocity. So again, tangential velocity is arc length divided by time. Let's take a look at it all together with that tangential velocity calculation involved. A ball on the end of a 1.5 meter string does 2.5 revolutions every 1.5 seconds. What's the ball's tangential velocity? The 1.5 meters is a radius. It's on the end of the string. So you're going to hold the string in one hand, the ball is going to be on the other. It's going to rotate around your hand. So that would be a radius. That looks like I got a typo there. Oh, I know what happened. I remember seeing this and fixing it everywhere else but right there. So that's going to be 1.25. Make sure, yes. I had it right in the math. I just had it wrong listed over here. 1.5 meters is the radius. The angular displacement is in revolutions. 2.5 revolutions. Again, angular displacement will either be in revolutions, radians, or degrees. And the 1.5 seconds, that's our time. We're going to be looking for the tangential velocity, vt. And again, the equation is vt equals s over t. While we do have our time, we do not have our arc length. We don't have s. So we're going to have to figure that out. First thing we're going to have to do is convert those revolutions into radians. Again, we're going to do that with dimensional analysis. 1 revolution equals 2 pi radians. So we're going to put the 1 revolution on the bottom. And we're going to put those 2 pi radians on top. And again, I forgot to type it in, probably because I was running out of room. But the 2 pi radian goes on top, the 1 revolution goes on the bottom. And again, the goal is to cancel out the revolutions and leave us with radians, what we need in order to calculate the arc length correctly. We can ignore the 1, so it's just 2.5 times 2. 2 pi, not just 2, divided by 1. And that's 15.7 radians. Once we have the radians, we can use the angular displacement equation to figure out what the arc length is. The angular displacement, which is the 15 0.7 radians is equal to S over R. The radius is 1.25 meters. Multiply both sides by 1.25 meters. 15.7 times 1.25 is 19.6. The unit for the radius will end up being the same as the unit for the arc length. And again, because of the way radians work, it's a function of the radius of the circle times the circumference of the circle. Whatever we have here in terms of radius will be the same unit that we have here for our arc length. Meters is typically the way to go, but this could be done with centimeters just the same, because you'd still have the same ratio that gives you your radians. We went in with meters, so we come out with meters here. But again, we need radians for that to happen. That relationship is not expressed with degrees. That relationship is not there with revolutions either. It only works with radians. Now we're ready to use the equation for tangential velocity, arc length over time. The arc length was 19.6 meters. The time from the question was 1.5 seconds. 19.6 divided by 1.5 is 13.1. And the units are just what you see in the calculation here, meters over second or meters per second. So again, you have to make sure that your angular displacement is in radians. So if you're given revolutions or if you're given degrees, you have to convert it to radians. Then you can use the angular displacement equation to figure out what the arc length is. Whatever unit goes in for the radius will be the same unit that you get out for your arc length. We had meters go in for our radius, we had meters come out for our arc length. Once you have that arc length, you can combine it with your time then to get your tangential velocity. This is an indication of how fast it's moving through the curve. An alternative way of solving out the problem is to calculate the circumference of the circle, then multiply it by the number of revolutions. This will give you the total distance that the object covers, and then you can use it in with the time that you're given to calculate the tangential velocity. I'll show you how that works. A ball on the end of a 1.25 meter string does 2.5 revolutions every 1.5 seconds. Same setup we had on the last one. What's the ball's tangential velocity? So again, same setup we had last time. The radius is 1.25 meters. The angular displacement is 2.5 revolutions. And the time is 1.5 seconds. We're looking for tangential velocity again. This time, instead of going through that process of converting the revolutions into radians, we're just going to use it to calculate the circumference. We're going to use the radius to calculate the circumference, and then the number of revolutions it goes through to figure out what the total distance is that the object travels. The circumference of a circle is 2 pi radius, 2 pi r. So 2 times pi times 1.25 meters. The circumference of my circle is 7.85 meters in length. I do 2.5 revolutions, so I'll take the 7.85 meters times 2.5 revolutions. And that means my object has moved through a total distance of 19.6 meters. Same calculation we got here for arc length, without going through the conversion from revolutions to radians. So if you forget how to do that, if you forget how to go from revolutions to radians, if you want to eliminate using the angular displacement equation, again, what you can do is find the circumference of the circle and multiply it by the revolutions. And that will only work if you do have revolutions. Once you've got that, then the math is the same. The tangential velocity is the total distance it covers, 19.6 meters, divided by the time that it took to cover that in, 1.5 seconds. You end up with the exact same velocity of 13.1 meters per second. So again, this is an alternate way of finding tangential velocity. It only really works when you have revolutions. You can use the radius to figure out what the circumference of one circle is and then multiply it by the number of circles you've traveled through to get the total distance traveled, which is your arc length. That can be used in that velocity calculation. Angular velocity is based on the angle through which the object moves, the angle that it sweeps out, not the distance. So it's a different way of looking at the velocity. While revolutions, degrees, or radians can be used in an angular velocity calculation, you can figure out the number of degrees per second. You can figure out the number of revolutions per second. Radians are still the standard measurement for the angle that's used most often in physics. So we're going to see radians used in here most of the time. Again, it doesn't have to be that way. If you own a record player, you know that a large LP spins at 33 RPMs. That is the angular velocity of the record. It does 33 revolutions every minute. That's what 33 RPMs means, 33 revolutions every minute. That's the angular velocity of the record. So it doesn't have to be radians or radians per second. It can be any of them, but we will typically use radians whenever we're doing the calculation. So a ball on a string completes 5.1 revolutions in 1.7 seconds. What's the angular velocity in radians per second? 5.1 revolutions, that is our angular displacement. Again, the angular displacement can be in revolutions, it can be in degrees, it can be in radians. The time is 1.7 seconds. We want to know the angular velocity. Again, you can do it in revolutions per second. And it would just be 5.1 divided by 1.7, and that would be revolutions per second. But this is asking for radians per second. So the first thing we're going to have to do is convert the revolutions into radians. So it's 5.1 revolutions times, and then a fraction bar. And it's the number of radians in one revolution that goes into our fraction. One revolution is 2 pi radians. So the one revolution will go on the bottom, again for unit cancellation purposes. And the 2 pi radians goes on top. 5.1 times 2 pi is 32 radians. It will have swept through 32 radians in 1.7 seconds. So to find that angular velocity, we will take the change in the angle, the 32 radians, and we'll divide it by the amount of time it took, the 1.7 seconds. 32 divided by 1.7 is 18.8 radians per second. Again, giving us an idea of how the angle changes. This does not tell us anything about the distance that it travels. It only tells us how much the angle changes, which brings up an interesting situation. Radius is not a part of the angular velocity equation. It's the change in angle over time. Because of this, we're going to see some interesting things happen when we start talking about different objects at different distances rotating together. The angular velocity is going to be the same for all 3 of these boxes on the circle. If all 3 of these boxes are traveling around the circle, let's say these are 3 carousel horses on a carousel. All 3 of these horses are traveling around this circle. All 3 of them are doing 5.1 revolutions every 1.7 seconds. All 3 of these are going to end up having the exact same angular velocity of 18.8 radians per second. This math that we did just right here. It would apply to all 3 of these carousel horses, not just the one on the outside or the one on the inside, all 3, because the radius doesn't matter. It doesn't matter that the green horse is 1 meter from the center, the red horse is 2 meters from the center, or the blue horse is 3 meters from the center. That doesn't come into the equation. There is no radius involved in any of these calculations. All that we need to know is what its angular displacement is, and we converted the 5.1 revolutions into radians, and then we're going to divide it by the time, 1.7 seconds for all of these. So they all have that same angular velocity of 18.8 radians per second. But the fact of the matter is they don't move at the same speed. For the blue horse on the outside to make a complete revolution, it has to follow the entire circumference of the circle around. For the red one to make a revolution, it will follow a much smaller path. For the green one to make a revolution, it will follow an even smaller path still. Each one of them will travel a different distance in the same amount of time, in that 1.7 seconds. And because of that, all three of these will have a different tangential velocity. Angular velocity and tangential velocity are two entirely different things. You can have three objects, like three horses on a carousel, that have the exact same angular velocities, but each one of them will have very different tangential velocities. Let's take a look at how it works. The 5.1 revolutions is 32 radians. We already did that calculation. We're going to figure out what the tangential velocity of the blue horse is and what the red horse is. I'm not going to do the green because if I typed in green on white, you wouldn't be able to read it very well. So just do the blue and the red one. So the radius is 3 meters. 32 radians was the angular displacement. It is equal to the arc length over the radius, 3 meters. Multiply both sides by 3 meters. You get an arc length of 96 meters. So to go all the way around this black line and make one revolution, or to go as far as they went, I should say, was 96 meters, not just one revolution, as far as they went, which was 3.2, I believe, or 5.1 revolutions. That would be 96 meters. Calculating the tangential velocity then, it is equal to the arc length divided by the time. Arc length is 96 meters. The time was 1.7 seconds. Its tangential velocity would be 56 meters per second, and that would be a huge number for a carousel. That would be the wildest carousel you've ever ridden. Let's do it for the red one on the inside. Again, the first thing we have to do is figure out what the arc length is. It still went through 32 radians, but this time the radius was 2 meters. Multiply both sides by 2. 32 times 2 is 64 meters. That would be our arc length. Now we're going to do that same tangential velocity calculation, but this time it's 64 meters. It goes on top, not 96. The time is still the same because both rotate in 1.7 seconds. 64 divided by 1.7 is 38 meters per second. So the red one is going considerably slower than the blue one is. The green one would be going even slower still. So as you move further away from the axis of rotation, the tangential velocity gets higher and higher. They start moving faster and faster. And again, that's so that they can complete that rotation over that longer distance in the same amount of time. It gives us a greater arc length when we're further away from the center rotation. So we have to cover that greater distance in the same amount of time. This is why if you're ever deciding what horse to ride on a carousel, if you want the fastest ride, you'll go to the outside horse. If you have a little child with you, you might want to choose the inside horse, one closest to the center, because it would move the slowest. This is also the reason why the grooves on a record are different from the outside to the inside, the length of the tracks, if you will, from the outside to the inside. On the outside, you're covering a much greater distance every second, so songs that are recorded on the outside of a record can take more space than ones that are on the inside, because on the inside, you're actually traveling slower in that tangential way.